Hello, Joby, and hello, Jonathan. We are still trying to fill the classroom here, so I will give it a few minutes before I start with the actual lecture. Good. I acknowledge you too.
Okay. So I was given a list. So
Yes.
just try number one and answer it if it didn't work.
Yeah, you want So now your test skill. No, not just the password, it's also. Did you underscore HC?
I just did this one.
Okay. Okay, good. Now you will want to set your own password. All right, although we are majorly incomplete, I would like to get started, if nothing else, with Q&A. That includes the folks online. If you have a question, just unmute yourself and please ask. Right, so I will do that in every session, or at the beginning of every session until the end of December. Beginning of each session is supposed to be your opportunity to go over material from the previous session. Is there anything that you have questions about? Okay. Hearing none. I asked you to A, check the Blackboard site on a daily basis, and B, to send me a short resume. There are, in theory, 16 students enrolled in this class. I received 5 resumes. That is not satisfactory from my perspective. Although there are no points assigned to that, it still helps me to know who I'm actually dealing with. So those of you who have not sent me the resume, please do so at your earliest convenience. Okay. Is there anybody in this room right now who has not managed to log into the computers here? Okay, good. Then let's get started. Session 2. This is a little bit different from how I have taught this course in the past 3, 4, 5 years. And the reason for that is that we have this break, and I want to make sure that you go into this break where we don't meet for the next 2 sessions with somewhat of a uplifting experience of what to expect in this course, rather than this very dry mathematical spaces stuff that we will then get to after the break. So today, not so much an overview of what the rest of the semester brings, but a more traditional introduction to what is GIS. I mentioned Tobler's first law of geography when we met last time. Does somebody remember? What does Tobler's first law of geography say? Somebody online? Georby, for example? Okay. I can promise you that will show up in the midterm exam. Because it's the first law, it's the most important law, it's the one law. It's the one thing that not the one thing that you need to know, but you definitely need to know that. Okay, so Oliver Tobler, eminent geographer, one of the fathers of quantitative geography, wrote a very obscure article in the early 1960s in a journal that otherwise is not known, if not everybody would be citing this first law. First law of geography says everything is related to everything else. But those things that are closer to each other, opening parentheses in geographic space, closing parentheses, are also more related to each other, meaning they are more similar in whatever measurement we are taking. Whether that's temperature, religion, car makes, anything. The reason it is the first law of geography is that if this wouldn't hold true, we would not have a discipline of geography. Everything would be distributed randomly, and if it's random, then we do statistics, we don't do geography. So geography is about spatial dependence. What we observe is a function of where we observe it. And I mentioned before that, from my perspective, geography is more a worldview than an academic discipline. The reason for that is that what it is that we look at could be anything under the sun, as long as we do it from that spatial perspective, with this geo-reference, this reference to a particular location on the surface of this planet. And so we are asking ourselves, why is it sunny right now here? And how is it different from what it is 200 miles south? So we are expecting that the rain that is the aftermath of Hurricane Ida, and it will come, we know that, and we don't know the exact path, but it will affect us. And so there's, and I will show you that equation a little bit later on, there's a relationship between the measurement that we are taking, the observation that we are doing, the location where we make that observation, and the time when we make that observation. Those three form the foundation of the geography of, the equation of geography. But what you see here is something that we won't really repeat in this class, but in a more advanced class when we look at spatial interpolation. So say we know measurements at a few locations. We try to find out what would be the value at this location where we have a technical measurement. And following Tobler's first law of geography, we say that whatever we are going to observe here is going to be more similar to what we observe nearby than to what we observe further away. We take all of these into consideration, but we give more weight to those that are close by. That's how spatial interpolation works, and it's again based on this first law of geography. The majority of you, we have a few newcomers here, so I can't speak on behalf of them, but the majority of you have learned in other college courses to think like a geographer. And when I say a geographer, I mean someone who is aware of spatial dependence. Of this, if you haven't heard actively about the first law of geography, you have implicitly applied it. So that's true in environmental studies, environmental science, and urban studies, and definitely in geography. But for that matter, in a whole range of other disciplines, as long as you put your spatial glasses on. So let's look a little bit at the notion of spatial thinking, and it shouldn't be too hard for you because you have imbibed that already with other courses that you have taken here as part of whatever degree you're pursuing. Spatial decision making takes place continuously, all the time in our life. We may not have put our nose into that fact, but like this morning, I come up from Westchester, I arrive at Grand Central, and I decide I'd rather walk than get a good subway. Do I walk up Lexington Avenue or do I walk up Park Avenue? That's a decision I have to make. And my decision is based on, my walk is less impeded by other pedestrians, smaller sidewalks and so on, than on Park as opposed to Lexington, although Lexington is a little bit more exciting. So on the way home, I actually might do Lexington because it washes away all whatever bothered me at work. By the time I arrive at Grand Central, it's just all the experiences walking down Lexington, which is one of the great avenues of the city here, will have done its cleansing effect. I don't need that in the morning, so I come up on Park. Spatial decision. Now that's a daily spatial decision, or whenever I arrive at Grand Central. There are other spatial decisions which are a little bit more complicated and which require more information to come up with a proper response. It's those more complicated decisions that we use GIS for, and why you actually sit it. So, for example, if we ask ourselves, where do we put the next waste incinerator? Or I just learned that the main prison the main jail in Manhattan is going to be closed because too many bad things happen there. Well, we have two options. You just release all prisoners and have a jolly good life, or you put them somewhere else. So where would you locate a prison? And who would be happy to have it in their backyard? That's a more complicated decision. It has to do with social equity, it has to do with making sure that it is indeed safe, and so on. All right. These are examples of spatial decision making, and on Friday in my lecture, I stated as one of my goals for you, what I want to accomplish, that you are able to do by the end of the semester, is to be a spatial citizen. somebody who not just indirectly and not knowingly makes special decisions, but somebody who is very aware of the spatiality of many decisions that we make on a daily basis and the consequences of it. Okay. Before we go into more formal aspects of what is spatial, let's look at a few instances of data collections that are aspatial, non-spatial. What you see here is a fake data set. I have to point that out, so don't draw any conclusions from that. It's a classic data set in the sense of we have a table that you would use Excel or another spreadsheet software for. The table is organized by a bunch of observations, the columns. A bunch of attributes, the columns, and a bunch of observations, the rows. So each row is a different observation. And what we have here is just a bunch of attributes that describe the results of a survey. Now, when you look at this, just looking at it in table form does not convey any pattern. So is there a relationship between the number of annoying people to the total population? Is it a certain percentage, or is it 3%? I don't know. Are annoying people more rich or more poor? Is there a relationship to the number of SUVs? These are all questions that we can ask in Excel, and we develop our correlations. But just looking at this table, we don't see any kind of pattern. We will be talking about data in detail and how we do measurements in 2 weeks from now. Okay, this is the same data set, but now put on a map. And suddenly you see, there is a relationship. All the northern districts belong to Whole Foods, and all the southern districts belong to Trader Joe. So now we immediately have some insights. This is just by visualizing the spatial relationships, which is what we do when we create maps. So the purpose of a map is not just to find from A to B, but also to see what is next to A, what is next to B. The first law of geography. Now that's a very basic map. We can now depict on that map any of the attributes that we looked at before. So here we have the population sizes. And we see that there are some bigger towns and some smaller towns. Typically, and that's another law of geography, far less, not less important, but far less impactful than the first law of geography. There was a German fellow called Chris Taller who came up with the best way to understand the distribution of phenomena. And first of all, what he came up with is that everything else being equal, no topographic influences, if you really abstract, you will find that towns are apart from each other in form of a hexagon. So that was invented in the late 1920s, early 1930s, somewhere in that ballpark. Since this was a German fellow, it didn't really spread very far. In the 1950s, when it was discovered by American authors, there were endless number of studies all over the world, particularly in the US and Canada, and they found indeed that if you manage to find a place that has not much of a history and not much of a varying topography, think of southern Canadian prairies, you will indeed find this hexagonal patterns of settlements. All right, that's one thing. The other thing that you will find is that you have, and that's what the name of the theory is, central places, central place theory. You have a central place, which is bigger, more important, and is surrounded by less important places. And there's a hierarchy of that. So depending on the scale that you're looking at, central places form the smaller neighborhoods of yet more central places, and so on. That's not really where I wanted to go. What I wanted to show you is that the moment we think like a geographer, the moment we think spatially, we take into consideration not just this table that we saw before here, sorry, this table, but we now put those table contents onto a map by virtue of where are we. So we can do geography only if we have that spatial reference. Now, here we don't really see any kind of spatial reference other than possibly the county and the state. And for the state, again, we would now have to see where is that state? How is it distributed and which counties belong to what state? Now that's what we see on this map. Here we have the individual counties and the two states. Remember, fake. Okay. We can now put onto that map any kind of visualization of any attribute we choose. Whether that's the population size, the number of annoying people, the number of SUV, the income, it doesn't matter. All of these we can now depict on that map. And where we struggled before to see any kind of relationship, now that we put it on a map, things start to fall into place, things start to make sense. I've been a geographer for a while, and back when I studied geography, nobody had an idea of why I did it or what I could possibly do with it. And back then, I was not in the position to tell people, well, you know about Google Maps, because it didn't exist. So the memory that people had of geography was this dreadful memory of sitting in the back of a car and the parents struggling about what direction to drive and when to turn left or right. And that required map reading, and map reading was scary and yeah. Okay. So not a particularly good experience. Things have changed dramatically in favor of geography. Because many companies, and arguably the first one to really jump onto that bandwagon was Google, recognized the value of spatial information and making sense, reasoning about where do we make what kind of observation and how does that help us to predict things. They then made it easy so that we don't have to read maps, they just tell us through the loudspeaker in the car, okay, and now next turn right. Different depiction. So we will be talking quite a bit about how to visualize data, regular data as well as spatial data. This is a so-called choropleth map. A map that uses different types of shading to fill in areas on the map. And there's a legend to that, which tells you that the darker the shading, the higher the percentage. And so now we see the number of SUV owners. And yeah, we would not expect Collegeville to have many SUVs. Students typically don't have that kind of money. And we would expect more SUVs up in Whole Foods than in Trader Joe's. So there is some fulfillment of expectations. A little bit of a surprise that Kingo County here has a good number of SUVs in Trader Joe land. Now, why is that the case? You might possibly want to have a look at their neighbors. Because remember, what we observe here is a function of what's happening nearby. So possibly looking at those neighboring counties would help us to understand why in a Trader Joe country do we have lots of SUVs. But now you're actually thinking like a geographer the moment you do that. Questions up to here? Hearing none. I've been using this slide for a few years, and it has never been more useful or truer to current reality than today. For two reasons. Reason number one is, so this is about tweets and about how you don't have to have explicit geographic data in order to find geographic data. There are geographic references in everyday speech. The same way that we are making geographic or place-based decisions on a daily basis. So this one is about being at some airport and making sure that we get to the right cinnamon bun place, because the place where that traveler is going to, that person would like to have some cinnamon buns. And it's one of those items that you get at airports all the time. Okay, good. Why is this particularly prevalent? For two reasons. Number one, I just finished a study analyzing tweets, trying to find out whether you can use Twitter data to substitute for US Census data when it comes to understanding the movement of people. So the US Census Bureau regularly asks, where do people live, where do people work? And then based on those two locations, we can reason about commutes. In a subset of those census questions, they will also be asking about what is your means of commuting? Are you traveling by car, public transit, bicycle, whatever? Okay. The problem with that is that only about 15% of all people's movements in the United States are commutes, which means 85% of our movements are not really accounted for by that very nice, very comprehensive data set. So can we find some other data source? And I was looking into Twitter, because when you tweet, there's always this locational reference. Where do you tweet from? And you just need to extract that information, either from where you specifically allow Twitter to record your location, or alternatively, where you make a spatial reference in your tweet, like these spatial references here. Now, the first one is really easy. If you allow Twitter to record where do you do your tweet, just get the cell phone location, which is triangulated from cell phone signals. That's very straightforward. For me, the researcher, I can use that X, Y, or that location and start putting it on a map. In 2013, Twitter changed its policy, and rather than you having to explicitly opt out, now you have to explicitly opt in to have your location recorded, which led to a 90% drop of that automatically recorded location information. So, and that study that I did, working with Twitter data for the Bay Area, San Francisco Bay Area, from all the tweets from 2010 till 2020. It's a huge number of tweets. The locational reference suddenly dropped. And it dropped so dramatically that it really affected the final outcome of the research. So back then, in 2011, 2012, although not as many people tweeted as nowadays, there were enough tweets with enough geo-referencing information to really substitute and actually augment, because we now have other 85% of the reference, to substitute for that official data. Whereas now, 2016, 17, 18, let's do it before COVID, there are not enough people whose location is automatically recorded to act as a substitute. In that case, you would have to go to the next step here and actually have to go into the text of the tweet itself. Now, that's something that's happening as a research agenda right now. And when you look at the conference proceedings or the don't really want to call it advertisements, but the publications that come out of companies that work with spatial data, this is one of the hottest topics. Using that locational reference, using natural language processing, artificial intelligence, whatever you want to call that, to extract those spatial references, even if you didn't give your permission. The tweets are open. Okay. So let's use those tweets and let's look for, given a certain XY location where that tweet was written, how often is a neighborhood name mentioned? So let's say we record a tweet here, we have the XY location for that tweet, and that tweet says Upper East Side. Chances are that if you go 2 blocks north, it will still say Upper East Side. If you head a little bit east and north, and now you have both Upper East Side and Yorkville. Or if you head a little bit south, you will get 2 tweets that are equally often Upper East Side and Midtown East. So there are some core areas where you will not get any other spatial reference but Upper East Side. And then as you move away from that core area, you get to those boundary regions where there's overlap with the next neighborhood. That's what we see here. This is a map of Boston and Boston neighborhoods. And the darker the shading, the more ubiquitous, or the higher the percentage of just this one name. So here we know we are definitely in a box cover. As we move away, it's not so definite anymore. This is something that GIS actually struggles with. So for us to say we are right now here on the Upper East Side, and when I walk back to Grand Central, I walk through Midtown East until I get to, I don't know, Carnegie Hill or something like that. Those are spatial references that we as human beings can handle, and we are also able to handle the ambiguity when we get into those boundary areas. GIS is not really good at that. GIS basically is based on computers. Computers, in the end, are working with bits and bytes, zeros and ones. You have to make up your mind. You are either here or you are there. You can't be in 2 places at the same time. So Computers are very good in situations that are unambiguous. The computers struggle, geographic information systems struggle when we get to areas where there are no well-defined boundaries. Geometric boundaries, or in this case, attribute boundaries. If you drive up Hudson Valley, at some point of time you come to the Catskills. Is there a place where it says there's a street sign, now you're in the Catskills? Is there a line drawn on the ground? Now you're in the Catskills? No, no such thing. So, mountainous regions, for that matter, the boundaries in the sea. Where does the Gulf of Mexico end and where does the Caribbean start? Those are very fuzzy, vague boundaries, and for that matter, no boundaries at all. And those are things that computers struggle with. Humans don't. Humans are really good at dealing with ambiguous information. Okay. How are we doing with time? Rather than actually, we will do that, go into RPS online when after the, so there's a first part lecture, second part lab, and the labs, they are all RPS online. So we will go through this together as part of the lab. So let me jump over this demo here. Questions up to here. Those first law of geography, the difference between spatial and aspatial or non-spatial, the notion of spatial reference, explicit and implicit, and ambiguous and unambiguous. Okay, so what we covered so far is the basis of something that we refer to as the georelational principle. And I was showing you this table here. This is a bunch of attributes that describe what we observe at one location or the other. And then there are the geometries. The geometries give us the spatial footprint for where do we make one observation or the other. So each of the previous rows was one of these geometric entities. This is about organizing data and finding the spatial element in data to then start reasoning about it. The kind of reasoning that we did when we looked at this thematic map or this thematic map. Okay. Now we move, this is the data perspective. Now we move on to says here spatial relationships, but what I would like you to remember from last Friday is this unofficial subtitle for this course. GTECH 201, Geography, the Relationship Game. So the first relationship was what we saw before, the relationship between locations and what we observe at those locations. Now we are looking at the relationships between locations. So in the first instance, we had a very myopic view. We looked at one location and what we observe here. And then we erase our mind, we go to the next location and look what we observe here. From now onwards, from this slide onwards, we are actually looking at the relationship between what we observe at one location to what will be observed at another location. Those are referred to as spatial relationships. Spatial relationships can be either quantitative or qualitative in nature. The quantitative ones, and we will see lots of exceptions to that rule, is what we typically refer to as distance measurements. We measure distance in miles or meters or hours or whatever, or directional relationships. If I get out of Grand Central, out of Metro North, and I want to head to Hunter, then I better head north. That's a direction. And northeast is qualitative. 350 degrees, because the Manhattan grid is actually not exactly north-south, but at somewhat of an angle, following the shape of the island. So if I had 350 degrees north from Grand Central, then I will be able to move along Park Avenue until I get to the 68th Street. Okay. This here is about a different kind of spatial relationship. Those, what we see here, are referred to as topological relationships, and we will go over those in some detail in a few weeks from now. Topology is a branch of mathematics which you will encounter Friday next week when we talk about mathematical spaces. It's one of those more abstract spaces where we actually don't do measurements. There's no unit of measurements in measurement in topology. All we can say is something is equal to something else, which means they are 100% congruent. If you take your Census Bureau information about New York County, which is the official name for Manhattan, and you look up, I don't know, some housing characteristic, and then you look up some income characteristic. Those two characteristics use exactly the same spatial footprint, that of New York County. And there's the first data set uses the same spatial footprint as the second data set. They are identical, equal. This touching relationship. Let's again use our US census data, and now we are looking at data from Queens County and Kings County, also known as Brooklyn. I purposefully move away from Manhattan because what we are now looking for is a touching relationship. Touching means they share a boundary. Queens and Brooklyn share a boundary. There's not a single street in all of New York City where the same street segment is at the same time in Queens and in Brooklyn. It's one or the other. So we have two entities, entity A, entity B, and they are not separate from each other. They are definitely not equal. They touch each other, and touching means they share a boundary. And we have an overlapping relationship. I don't know how many of you know, but there are parts of Manhattan, officially known as New York County, that are actually north of the Harlem River, on the river delta, in what we know as the Bronx. So you can have a data set that describes the coastlines. You have the coastline of the Bronx, you have the coastline of Manhattan, and those are two different entities. And now you take the census data set that describes Manhattan, New York County, and put that imprint on top of your coastline map, and suddenly it goes beyond the island of Manhattan because of those spillover census tracts over there. And in the Bronx, or what we know as the Bronx, but actually, officially, it's not. So that's an instance where, how do I do this? Well, I guess B is Manhattan, the island, and how do I? B is New York County, and A is the Bronx. And parts of New York County overlap with the geography of the Bronx. So there's an overlap between them. What the overlap means is, in this little sliver here, we have observations of both A and B. We are in the Bronx, but we observe data from New York County. When I say we are in the Bronx, I mean we are in the geography of Bronx, but not in the political unit of the Bronx. Two different things. So the difference between those two is, here is a shared boundary. Here is a shared area. Shared line, shared area. Two different things. And then we can have a situation like this one here. All of New York County, all of the Bronx, all of Kings County are in the state of New York. So A is the state of New York, B is Kings County, Brooklyn. Brooklyn is squarely inside, completely engulfed by the state of New York. The relationships here are from identical. Every point inside one is also inside the other. No point outside one is outside the other. The boundaries are congruent. Then we can have a situation where here's A and here's B. Those two are now completely separate, not touching, not overlapping, not anything. We can move from this completely apart to touching, and it's a very delicate movement, because touching allows us not to have an overlap. Touching really means only shared boundary, like the one between Queens and Brooklyn. If we move B any further, now we are not touching anymore. Now we are overlapping. And if we move B even further than that, then B is completely inside. So these are qualitative differences that we make use of, again, on a daily basis in our decision making. That from about 70% of all GIS functionality is based on this one stuff. The kind of spatial relationships that we try to reason about. Now, what you see here is something that you could not address in Excel or Microsoft Access or any other AutoCAD or anything like this. These kinds of spatial relationships can only be reasoned about by geographic information systems, GIS. That's what's so special about them. So, yes, we want to be able to look up the various attributes of counties and Trader Joe land and Whole Foods land. That's one possibility. It's just this lookup. But the lookup we had all the information in the spreadsheet. We had the county name, we had the state name. Everything was there. was not as easy to reason about as we do when we visualize the results. But the reasoning itself could be done in a spreadsheet. This reasoning that you see here cannot be done in a spreadsheet. There's no functionality built into either databases or spreadsheet software or word processing software or anything else out there other than GIS that allows us to reason about these kinds of spatial relationships. The same is actually true for distance relationships. If you want to measure the distance between here and Grand Central, or here and Los Angeles, you can't do that in a spreadsheet software. Because the spreadsheet software, well, you can put the distance as an attribute in there, but that's just a lookup. That's not reasoning about it. It's not a deriving new information. You want to derive new information, looking at spatial relationships, whether they are quantitative or qualitative. That's when we use geographic information systems. Just see what I have in the next slide. Remember I was talking about the disjoint, I was talking about A and B, well, there we have it. Those kinds of relationships, all the examples that I gave you were about areas. How does one area relate to another area? Now, they also work with lines, or with points, or a combination of those. So we can ask, is Columbus, city of Columbus, in Ohio, the area, the state of Ohio? And the answer is yes. Is Tacoma, the city of Tacoma, in the state of Ohio? The answer is no. So we can ask that about points and lines, points and areas, lines and lines, lines and areas, and so on. Any combination. Yeah, let's use this slide here to see whether you have questions. I could ask for the previous two slides, do you have questions about spatial relationships? Or I could ask you, okay, look at these questions here, and can you answer them? If you can answer them, then you got it. If you can't answer them, then we need to talk about this. Yes?
I have a question. You talked about topology. Are spatial relationships topology? Basically, are they the same?
So we distinguish between quantitative and qualitative spatial relationships. Qualitative, all the topological relationships are qualitative in nature. As we will see, particularly in the lab exercise next week, distance relationships can be both quantitative or qualitative. Like directional, I was talking about north is qualitative. 350 degrees is quantitative. A distance far away is qualitative. 560 miles is quantitative. The one you just looked at it. Hang on a sec, I finish my sentence, then I take the question from the web. The previous two slides are also called topological relationships, and they are always qualitative because there's no qualitative spaces, as we will see Friday next week, before we introduce any kind of metric, any kind of measurement. Remember I said You can be far apart from each other. This A and B are apart from each other. And it doesn't matter how far apart from each other they are, as long as they have no overlap and no shared boundary, they are apart. And then you move them ever closer, and at some point of time, there is a qualitative difference, because suddenly they share a boundary. Let me take the question from the web first. There was a question? Hearing not? Your turn.
So this is a bit of a weird question, but if you say something like the store is 5 blocks down the road,
Yes.
is that quantitative or qualitative?
I would call that quantitative.
Okay.
So when we say something is 5 miles away, even if it is 5.1 miles away, we still call it 5 miles away.
Yeah.
Same thing with the blocks. So in New York, you would ask, okay, do you mean a long block or a short block? East, west, or north, south? But then we are New Yorkers. No, we walk. It's 5 blocks. We don't really care whether it's short or long blocks. So we just measure in form of blocks, and then 5 is less than 6 and more than 4. Quantitative. By the way, no weird. That was not a weird question. Yes.
Due to the ambiguity of words footnote 4, how often is overlapping used versus touching?
The question was, among the topological relationships, is one more common than the other? And the answer is, in short, I don't know, but looking at just the range of GIS applications, everything that you saw on these 2 slides is commonly used. These are common spatial queries. It really depends on what is it that you're trying to find out. For example, the neighborhood relationship is, and we will be talking about that when we get to our mathematical spaces. A state is either neighboring one state or it's not. So Vermont is neighboring New York. Vermont is not neighboring Pennsylvania. We could argue that Vermont and New York have lots in common, and argue that New York and Pennsylvania have a lot in common. But then, when we look at the commonalities, it's that in Binghamton, close to the Pennsylvania boundary, you have similar political affiliations, similar leisure habits, and so on. And then on the other side, when you get too close to the boundary between New York and Vermont, again, we have similarity. The further something is apart, the smaller the similarity, first law of theorem. Now, because we are now in topological space, we just count are we first degree neighbor, second degree neighbor, third degree neighbor, and we don't really measure whether that degree is a 5-mile sliver or 500 miles apart, like Louisiana from New Mexico. There's only one state in between, but it's a very big state. So suddenly, second degree neighbor really means being in a different world. What I like best about our conversation right now is that I make you think about that. you have a bunch of different analysis options in GIS. And part of the challenges when you get to the cartographic studio is in the second half of the semester is trying to see, okay, what is my research question? And how does my research question translate into GIS operations? Do I assume something on the quantitative side or on the qualitative side? Do I look at those topological relationships, or do I do actual distance metrics measurements? Okay. So what this slide here refers to is when you sit in a car or you're on your bike, you're sitting bike, and you try to get from A to B and you have never been on this route before. So you use your cell phone or your in-car navigation system to follow the instructions of where to ride. The cell phone or the in-car navigation system gets some GPS coordinates. Those GPS coordinates are more or less accurate. Typically, let's assume less, unless you are in an area with really excellent cell phone connection where you have 15 different cell phone towers that give you down to the foot accuracy. So typically, you get some measurement, and then a few seconds, the next measurement, a few seconds later, the next measurement. Those points now have to be referenced to somewhere on the road. And imagine you follow the instructions and say, okay, based on what the system receives as where you are right now after 30 feet, please turn right. And you do that, and you drive right into the wall of the house. What you really want to say is, no, not after 30 feet you turn right. At the next intersection, you turn right. So you want to make sure that regardless of what measurements come in, they are always then remapped to locations on the road network, or bicycle park network, or whatever it is. What we also want to do is to make sure that we have the right degree of connectivity. Let's look at this example here. We have two lines, A and B. If these are streets, you might happily drive on line A, and then when we get to this intersection, turn into line B. If these are two subway lines, these subway lines may intersect on a map, but not in reality. In reality, what we would need is a station at this intersection. Otherwise, there is no way to jump from one train onto the other. I mean, not unless you are in some 1980s romantic movie. So this is again a topological relationship. Do we allow for the intersection here, or do we say these two lines virtually overlap, but in reality don't? If we allow for a change, then we have to insert a node here. We have to say, this is not a line segment that goes from here to here, it's actually one that goes from here to the intersection, and then from the intersection to the next. Two different things. If they just visually, graphically overlap, that's not good enough. Not for changing lines. It's good enough for other purposes. If would that be? One is a river, The other one is the path, the track of a hurricane or tornado, thunderstorm, whatever. And we try to find out, okay, where do the two intersect? They don't really have to physically form a connection. We just try to find out along with that storm, where does it rain and where does it start to flood? And it floods and where the river is, where the valley is. So, coming back to your question, the relationships that we are looking at are right now described as abstractions. And we have to take our actual research question and translate that into those abstractions of spatial relationships. I mentioned scale before as one of these geography, the relationship game, relationships. So when we deal with scale, scale has multiple meanings in the context of working with geographic data. There's the traditional map scale that you encountered in, hopefully encountered in some 100 level class, where we're presented with a map, and on that map it said 1 inch equals so many miles. That's the high school level map making scale. A very different form of scale, or very different interpretation, understanding of scale, is one that is really important to us in the world of geographic information science. Is what is the smallest element that is recorded in our database? So if you have a map of the rivers of the world, because it's the rivers of the world, it's not going to have the small rivers. It's not going to have the Bronx River. It might have the Hudson, but given that it's a world map, probably not even the Hudson River, although that's a sizable river by most people's standards. It will have the Mississippi. It will have the Colorado. Those are major rivers on a world map. Now, the Bronx River is nothing to sneeze at. It's important for folks who are living there. It was important for Mr. Bronx, a Danish citizen who bought the land from the locals back when he arrived, and started to dam that river to run mills to fetch the beach. Okay, that's so. It's a function of what is it that we want to work with that determines what are our data needs. And is the world map of rivers good enough, or do we need a more detailed? And there are beautiful maps of USGS, Geological Survey data of just the river systems in the United States. Very detailed, very tiny. Okay, then we have this notion of the scale of analysis. This is more at the conceptual level, that's not at the data level. So the second one, the spatial resolution, refers to what's the smallest element that's still stored. And from there we can go upwards to the largest, to the Amazon. But the smallest, what's the smallest river that's still there? Either in length or water volume or distance from one shoreline to the other or whatever. We use that spatial resolution also when we talk about data that we typically acquire in the form of photography. And you have come across resolution here. How good are the pictures that you take with your cell phone? Is it 1 megapixel, 10 megapixels, 100 megapixels? And now using those lenses and directing them at the same object, how many pixels does this object consist of now? So the finer the resolution, the more detail you have. The scale of analysis is more at the conceptual level, where we ask the phenomenon that we are looking at what scale is it occurring? And last Friday, I was giving you this example of coastal geomorphology and the action of an individual wave as the once, not even in a lifetime, once in a geologic era, action of a mega tsunami. So at what scale do you do your analysis? When you look at the politics of the United States, do you do that on a state-by-state basis? Or do you do that on an electoral district-by-electoral district basis? And there are a few thousand of those in Manhattan, so that's very fine. It's the scale of our problem, our research question, that determines our needs with respect to the scale of the spatial resolution. So the third scale here drives or determines your needs for the second scale. The top scale, the map scale, is then just for communication, for creating the final map. Geography, I kept saying, is a function of location. But, and I mentioned that once before, and now we get to that again, geography is also a function of time. What we observe now at this one location may and most likely is different from what we observed in the past or will observe in the future. It's a strange thing because geographic information systems really are good at static snapshots. So a map represents one time span, one moment in time. Geography, the discipline, started about 100 years ago to move from where a spot to how did this come to be here. This process orientation is something that GIS struggles with. Process means change over time. And that's a lot more complicated than just a snapshot. Snapshots are easy. Let's look at this aerial here. I'd like you to interpret this. First of all, what are we looking at in the first place? Describe the source and describe the phenomenon that we are looking at. Yes?
It looks like it's highlighting the expressways that are around Manhattan.
Okay. So the expressways are laid on top of what? What gives you the spatial reference? How do you know where you are?
It's on part of the map, well, map of part of New York City.
Satellite image. So this is actually a photograph. And yes, I believe I would agree that it's a satellite image rather than an aerial. As such, it's somewhere in between the photo and the map. The It's like an augmented photo where we then put the one pertinent information, the freeways on top. Now, the photo gives us some context. Could I get a few keywords as what do you see on the photo? Along the highways, you see a lot of parks. That's already a lot of interpretation, correct? Yes. So there seems to be, it's almost as if the freeways are purposefully going through the parks. Could be the other way around, that the parks got created where other land users really have to do, but whatever. All right. So, good. What else do you see on here? Yes.
General locations like Upper East Side, West Side.
Okay, so you are geographers. I mean, you really move into interpretation right away. So you can depict the property sizes. I'm not so sure that you actually can. I think what you see is the street blocks, which are relatively equal, but then within the street blocks, there's varying degrees of density. And again, if you have more green inside the blocks, then you assume fewer housing or whatever. Mind you that, especially up here when we get into Harlem, those green areas are actually between NYCHA housing high-rises. So the population density is the greatest on anywhere here on this map. This area has the highest population density, although it's also relatively green. Okay. Could I direct your attention to the water bodies? When I moved to New York some 20 years ago, one of the things that really intrigued me is how much it is determined by water. And the geography of New York City water still has to be written. What kind of water bodies do you see? Rivers. Would you dare to label them? Hudson River, East River. What's this here? That's the Long Island Sound, yes. And then
The Dutch name? Is that the one with the Dutch name, or is that the
it's just the Harlem River. It's what we know as Harlem River, which it's not really a river. It's the same way that the East River is part of the Hudson, with Manhattan just being an island in the Hudson. The Harlem River then is the northern boundary of the island. Geographically or from physical geography perspective, just part of the Hudson River. But human geography perspective, the connection between the Hudson River and the East. All right. Now let's look a little bit more at this part here of the water body. Do you see boundaries there? Apparently not. Yes.
Well, I see for LaGuardia Airport, there's a much more
Okay.
developed boundary.
So what you are referring to is the shoreline.
Sure.
And of course, we have shorelines everywhere where land and water meet. And yes, you are right, in something like a mega structure, like an airport, those lines are very prominent because they are unusually straight for something natural like a river or a sound. Okay, What I was actually referring to are the boundaries inside the water.
So there's a depth, it looks like there's some sort of depth distinction.
See this line here? How do you explain that? Is that a political boundary? Is that a natural boundary? Is it a boundary? What is it?
I interpreted it as the imagery being labeled for separate imagery at different times, like the coloration
Comes after this slide. Right. So what you observe here is actually a composite of various satellite images. And whenever a satellite takes an image, somewhat like a photograph, it looks at the reflectance values and then standardizes them. And water is like water, is like water, is like water. In this era, and water is like water, is like water in this era, different time slot. Now that they have been composited, put together, mosaiced, now water is next to water, but depicted using different reflectance values. Yes?
So what time of day is darker and what time of day is the water?
I am not even sure that it's time of day. I'm fairly confident that those two satellite images are many months, if not some years apart.
Oh, so like which ones?
I have no idea. They don't tell me that, by the way. When you look at the bottom of, well, I cut it off here. So when you actually go to, this comes from Google, at the bottom it tells you what are the data sources. But it doesn't tell you which part of what you are looking at is coming from what data source. It's just telling you the generic data sources. Okay. So, the reason that I brought this up, time obviously matters. Because time gives us different pieces of information. And when we combine two data sets from two different times, the result typically is nonsense. Because those boundaries don't exist. We're doing the time. 11:08, 9:45. Let me just see how far am I in here. 17. Okay, who needs a break now? One. That's. Let me go over locations. So, when I started talking about spatial versus aspatial, the difference between geographic data and non-geographic, I said, well, the basis is that in order for it to be geographic, we need to have a locational reference. Something that points us to somewhere on the surface of this planet. So we need to talk a little bit more about locations and how do we determine locations. In the past, as in this resurrection of old era surveying, in the past, those locational references, the knowledge about them, used to be state secrets. The mapping was a function of the government or of the military. And in many countries, that's still the case. Nobody in this room, we have Sanisha here, but I believe if you're Nepalese, all right, you also are not allowed to make a map of anywhere in India. Only Indians are allowed to make maps of India. They may be allowed to make a map of India, but they are not allowed to publish it. The publishing of any kind of map of any kind of mapping information is a function of the Indian state. And by the way, that's not just India. There are about 100 countries around the world that feel similar about it. So location is something that's considered to be extremely valuable, sensitive. Not the least because until very recently, to determine one's location accurately was really hard to do, was expensive. And having that knowledge really put you at an advantage over anybody else. Things have changed a little bit with the commercialization of something that originally was called the Global Positioning System, GPS. Shortly after Sputnik in 1961, the United States woke up to the space race and really moved ahead and became the dominant power, not just on the ground, but also up there in space. And so they were the first ones to put up a system of satellites whose sole purpose it was to be exactly at the same location above ground all the time. So because the Earth is spinning, those satellites were spinning as well, but synchronous to the Earth spinning, so that they seem to be what's referred to as geostationary, always at the same location. And they are fairly high up there, 36,000 kilometers. That's in the order of about 15,000 miles, something like that. It's really way up, which means that it's relatively easy to get their signal, because there are always a few of them above the horizon. And what a GPS receiver does is very similar to what this fellow here did 200 years ago. It triangulates between the signals from known locations. So if we know where this satellite is, and if we know where that satellite is, and a third one, then we can use geometry to calculate where are we. The other thing that we need is we need to know how long does the signal take from that satellite to us. So we need to have a very good clock on the satellite and a very good clock down in our sensor, and they need to talk to each other and compare timings. Okay, so now we get the distance and the direction. Now we know where we are. Here, that was put into space in around 1990, and then at some point of time, the data was released so that everybody could use it. Since then, we have a multitude of such systems, not just the American one, but well, the Chinese, the Russians, the Indians, the Europeans. They all have their own systems up there. And a good GPS receiver, not necessarily this stuff here, but one that you purchase for a few $100, can receive signals from all of these satellite systems, which gives you plenty to choose from, which improves the quality of the data that you're working with. We now have GPS sensors also in our smartphones. They are not terribly good, but good enough, especially if you are outside of the traditional cell phone area where you cannot work with the triangulation between cell phone towers. So once you're in the Adirondacks, your cell phone is a brick. You cannot place a call, but you can still receive a GPS signal. Okay. The GPS in our cell phone is not particularly good. The high accuracy that we are used to getting instructions when we sit in a car and are told when to turn, is a function of nearby cell towers, which are much closer and hence give us a much better calculation of our exact location than the GPS satellites further away. But a professional-grade GPS gives us accurate information anywhere on this planet, and if it's a good one, say down to a foot accuracy, which is about from a geographic perspective good enough. Anything better than that is civil engineering requirement, but not a geography. Okay. So you receive a signal, and that signal tells you a particular location. And if you were to pull out your cell phone now, you would get a location somewhat like this one here, which measures degrees west of Greenwich and degrees north of the equator. And you can be confident that you are somewhere within 73 degrees west of London and 40 degrees north of the equator. That's a safe bet. Any GPS, any cell phone will give you that level of accuracy. The 2, 3, 4, 5, 6, 7 digits after the comma, well, the further you move to the right, the more fake it is. Or in other words, you just sit still and you record a signal, a location, and a minute later you record again, a minute later you record again, and then this evening you record again. Possibly every minute in between, and you will have at least 100 different coordinates. You haven't moved. The cell phone hasn't moved. But according to your coordinates, you have moved. That's because the cell phones are not really that good. So the further you move here to the right, this seemingly high accuracy is fake. It's just internal calculations that are with rounding errors. Because 7 digits, that's 10 million. 10 millions of a degree would get you into fractions of an inch, millimeters accuracy. They are just not that good. Okay, but let's assume you work just with the first 3 or 4 digits after the decimal. So we have one location, which gives us something down to the meter or something like that. And then we move about, we get out of this door, we take another measurement. That ought to be different with a decent receiver. Then we turn left, we take another measurement. Then we turn left and we take another measurement. Then we go downstairs and exit Hunter College. And we walk around the block. We always take measurements. Now we connect those measurements. And now we have the actual line of our movement. So we can have point information. We can have line information, where we just draw straight lines from one measurement to the next one. And if we walk around the block and then enter Hunter College again, we can have area information, which gives us the size of the street block. 68th down to Park, up to 69th, over to Lexington, down to 68th, back to Hunter. So we refer to either point data, line data, or area data, describing 0, 1, or 2-dimensional geometries. The points, the lines, the polygons are all made up of individual measurements. So a line, and apologies to those folks who are online, I'm now going to draw lines and areas on the whiteboard. A line is the straight line between 2 points, a start point and an end point. Start point and an end point. And it so happens that if we do those combination of lines, start point to end point, start point to end point, start point to end point, where the last end point is the same as the starting point of the first line, now we have formed the boundary around an area. So we can describe just points, we can describe lines, we can describe areas. Areas are made up of lines, lines are made up of points. Everything boils down, comes back to individual points, locations. Those very same locations that we started out with this fellow recording location. Except that we are now doing that ubiquitously all the time. Key. Those locations, the points, the lines, the polygons, are referred to as vector data. That was a see your hand. Friday next week, when we get into mathematical spaces, we will be talking about vectors and what is a vector. And so we will start somewhere with logic, and we move into sets, topological spaces, all without any kind of measurements. Then at some point of time, we start introducing coordinate systems. And once we have a coordinate system, we can put points into that coordinate system, and now we can also connect points into lines. And all of these have a reference to the origin of the coordinate system. Those relationships between the origin and the destination are referred to as vectors in n-dimensional spaces in mathematics. You had a question?
Yeah, why polygon? Like it's not a rectangle or a...
Well, it could be any shape.
Okay, so it's just an example.
Any, it's called a polygon. At a minimum, you need 3 points, a triangle. But it could be the island of Manhattan is a polygon that consists of many thousands of floating points. When you draw the individual zigzags of the different Ks and so on, Ts.
It's more just a generic...
Polygon is the generic mathematical term. Now, and we'll get to that again when we talk about mathematical spaces. Remember, when we talked about topology, I said what's really important is, are they apart? Do they touch? Do they overlap? It so happens that what we do in the world of vector geometries, we describe areas by their boundaries. So, the boundaries are important. We never describe what's inside. We describe it in the form of attributes. But there's no further geometric information about what's inside this polygon or inside that polygon. The polygon is defined by its boundary. The same way that a line is defined by its boundary. The starting point and the end point. We don't say anything about those space in between. So this notion of boundaries is really important in the world of vector GIS, and for that the world of GIS. Okay, so that was, we ended with points, lines, and polygons from spatial vector data. Now there's a very different way to look at the world. Still dealing with locations. And this is where, when our data sources are not individual point measurements, our data source are snapshots of many locations at the same time, as what we are doing when we take a photograph, an image. There's a course that's parallel to this one, GTECH 202. It's called Earth from Above, which is really complementary to what we are doing. So this is, the proper title should probably be Introduction to Remote Sensing. The same way that we have Introduction to GIS. And in GIS, we typically deal with those individual coordinates. Introduction to Remote Sensing deals with not really coordinates as much, but very much about space. But space captured in a very different way. So, what all of these different data sources, the virtual globes, the drone imagery, the cell phone here, what they all have in common is that the data there does not consist of individual separate locations. The result of all these data capture mechanisms is an image that has a certain resolution that we talked about before. Resolution measured by the size of the pixel and how does that size of the pixel refer to an element on the ground. Now that's a function of how far away is this object that you're taking the picture of. If I take a picture here of this disk, that's a 6-inch distance, I have a very high resolution. If I take this tomorrow when I fly to California, and out of a plane window, I take a picture down on the ground. Now I'm 30,000 feet above ground. Now each pixel represents, I don't know, quarter mile on the ground or something like that. So the pixels are individual picture elements, typically organized in form of a grid. Very similar to a spreadsheet. So we have a picture element, next to a picture element, next to a picture element. By the way, but when you look at your screen, you're also looking at pixels. Yours in front of you consists of, I don't know, 1920 by 1080 pixels or something like that. What this projector projects here, what looks like an underline, a line, is actually not a line. It's not coordinate here, and then draw a straight line. What it really is a blue pixel next to a blue pixel next to a blue pixel next to a blue pixel. So all of this consists of pixels. That's a very different way of looking at it. Especially if all you see is blue versus black versus red. You are human, which has certain advantages, which means that you don't interpret these as arbitrary lines. You interpret these as characters that are part of a text that convey information to you. All of that is happening between your two ears. And it's stuff that computers really have a hard time with. What a computer can do amazingly fast is white pixel, white pixel, white pixel, black pixel, black pixel, black pixel, blue pixel. Very straightforward. It can do those operations millions in a second. And that's what remote sensing consists of. Now, you see whether I have that up there. I jump over this one. It's more important to discuss with you, when would we use what? So, coming back to this thinking about what we just learned. How do we apply that? When would we use individual locations, GPS measurements or similar, and when would we use this stuff? Let me give you an example of this stuff. So this is raster data, vector data. Yes?
Use vector data for more accurate or to draw like more accurate analogies between them. Vector data can get like small preview or
Okay.
not as accurate.
So you altered your answer. You started saying something where my response would have been not right, and then you corrected yourself or you augmented yourself and then a yes. That's it. You used the word boundaries. Remember, that's what I said. In vector data, the boundary of a line is the start point of the end point. The boundary of an area is the perimeter of that area. And those are the things that we actually store in vector GIS. Which means that vector GIS is whenever we deal with boundaries. Now, give me application areas from your field of experience. When do you run into spatial boundaries? And when do you work with situations where it's hard to determine spatial boundaries? Yes.
In archaeology, you sometimes have to map out the ruins of a monument, and sometimes it's hard to spot where exactly the area is.
Okay. So in archaeology, when you look at something that's underground and there was a structure 2,000 years ago, but now it's not really discernible anymore. You just see undulations in the landscape. That is an example for when you would use what?
Like most would use vector.
No, for that you would not use vector. Because now we are working with these undulations in the ground. That's not a well-defined boundary.
But is raster better for that?
That's better for that. Yes. And I want to hear the next response, and then I will explain why. You had a question on your hand up? No? Yeah? Okay, sorry. All right, so we use raster data whenever we are lacking boundaries. Man-made features typically consist of straight lines and sharp angles. Natural features typically do not. So we use vector data whenever we deal with man-made features. We use raster data whenever we work with natural phenomena. Now, your archaeology example originally obviously was a man-made feature. That wall of the temple and wall erected 2,000 years ago. But that temple is, we don't know even where it is. We just look at the landscape. All we see now is there is this area that looks different from the surrounding. We would typically use something called sonar or LiDAR, which both of these words relate to what you know as radar, sensors that use electromagnetic spectrum to receive pixels of different reflectance values. So what they receive is observation, 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 and all the observations are at equal distance to each other. So that like the pixels on your screen, we know exactly where the next observation is. We don't need to do measurements. So we don't need geometries. But if we have an observation that says, and just measure in 2 feet beneath the ground, 3 feet, 5 feet, or 0. 0, 0, 0, 2, 2, 2, 2, 2, 5, 5, 0, 0, 0, 0. Then you say, okay, this is This is not natural. First law of geography, things that are next to each other should be similar. What I just described were situations where take a measurement, you take a measurement, you take a measurement, they are all similar to each other. And then suddenly you have a jump. And then we have again similar, similar, similar. So now we have determined a boundary, very indirectly. But it's a boundary where we don't have the exact coordinates. All we see are likewise values next to each other. And likewise values next to each other means of the same characteristic as opposed to those on the other side. So now we indirectly determine from our raster dataset there is something underneath that looks linear. Let's dig this up. But the source is not that somebody says, okay, here's the boundary of the corner of this temple, here's the other corner of this temple, and there's the line. We are not there yet. So that's why I said we start with raster data. After we have dug it up, now we translate it into vector data. Because now we have the exact coordinates. Right. Let's look at this one here. From this Earth from above class. This is a satellite image. It shows a settlement, and everything that's red here is actually vegetation. It's a so-called false color composite. So interpret red as being green or agriculture or whatever. Okay, it's fairly easy to see some roads here, settlement patterns of strange form of subdivision as they do it in Oklahoma and Nebraska and so on. You see all these vegetated areas, and then you see, and you really have to sit far back to see it. From here is actually not as keen, but when you see far back, you see there is some structure here along this line. Any idea what that is? I said Oklahoma, Nebraska. Does that trigger something? Something that is irrespective of whether there is vegetation or whether there is settlement. Yes?
Tornado path?
I didn't hear.
Tornado path?
Tornado path, exactly. Tornadoes don't care. What you see here is a path of destruction. It's where things got erased, boundaries got removed. Regardless of whether these are trees or households. And it follows a path. This is one of those barrier islands of the Jersey coast. We are looking at is what did this barrier island look like before Superstorm Sandy and after Superstorm Sandy. This is taken with an instrument that measures elevation. And its elevation, relatively small range, from 0, meaning literally 0, the beach, to 8 meters, 25 feet. Okay, so everything that's dark red is about 8 meters above ground. And you see here house structures. Now, this is again raster data. It's elevation next to elevation next to elevation. It's not a surveyor going out and measuring the corner of this house, measuring the corner of that house, and then drawing a straight line. So you have relatively straight lines of red versus green. But then those straight lines are also surrounded by yellow, which is a little less most instances. You may detect the road network on this island. All using raster data, which we typically wouldn't do for man-made phenomena. Superstorm Sandy happened. The barrier island got washed over. Few houses got completely washed away, but for that matter, everything else got washed away. This is why we use this LiDAR information, this elevation measurement. Because with one snapshot, you get to see exactly what's happening there. You don't need to send a surveyor out. You see exactly the houses, those are the unaffected ones. You see the unaffected roads, well, actually a little bit affected because the lines are not as straight anymore. It's similar to what we saw before with the tornado path. There's now a lot of debris that makes it harder to distinguish between the actual road and the front shelters and so on. Okay. But what you really care about is where the infrastructure completely taken out. And we do that with one single snapshot. That's the advantage of working with remotely sensed data. That's the advantage of working with raster data. Where we don't have the measurement of this corner, the measurement of this corner, the measurement of this corner. We don't have any geometries. All we have are attribute values, in this case elevation. We have elevation below 0, elevation below 0, below 0, 0, 0, 0, 0, and so on. We store nothing but elevation values. In the same way that on your screen, there is no coordinate system that says, okay, now you are at pixel 45 and 217. You don't see that displayed on your screen. It's a pixel location. We don't store pixel locations here. What we do is we say, this is the first pixel. And now we record attribute for as many pixels as this data set is wide, and as many rows as this picture is long. That's it. One coordinate, no geometries, a very simple word. Attribute. Not as pretty, which is what prompted you to give your first response, which says not as accurate. Well, accuracy is in the eyes of the beholder. It is not as good at depicting boundaries. And we really are interested in boundaries, and Western civilization is, then yes, we want to use graphic. All right. I think we have deserved a break. Quarter to 12. You think you can make it in 10 minutes? 5 minutes to 12? 5 minutes to 12. I will interrupt the recording for those online. We meet again and get started just with that exercise so that you all know how to get into RPS online.